can Zoom hear me? Can Zoom hear me? Jillian, can you hear me? Oh no. Hello, can you hear me? Dong Jie can hear me. Alvin Chi, can you hear me? Okay, Alvin Chi, yes, okay, great. So today we are going to continue our discussion on continuous random variables. And we are already at lecture 14. A few more lectures and I have to say bye-bye to you. So I just want to recap what we talked about last time. All right, so we have a certain random variable and we want to consider its conditional density condition on a particular event. Okay, so X is a particular continuous random variable, and the reading here is section 3.4 or 5, I don't know, something like that. Probably 4 or 5, maybe 5. All right, it's the one on conditioning. Okay, so X is a continuous random variable, and I have A, an event, not a random variable, an event with positive probability. This was where we left off last time. Probability of A is positive. If it is not positive, there are some technical issues. All right, so we say that, so this is continuous random variable. X has a certain probability density function fx of x. So that is the PDF. So we would like to try to understand. So the PDF actually gives us a quantitative view of the belief that X takes on values in a certain set X. But suppose Oliver told us that the random variable X actually belongs to some set. So that is some event. All right, so Oliver told us that actually X belongs to some set C. Okay, so that is actually some event which we can call A. All right, so that biases our belief about what the random variable is, because we are given some new information. Okay, so how do we then define this particular random variable f of x given A? All right, so suppose now we know, or we can condition on the event, we know that X belongs to some set C, okay? Or we know roughly that we know A occurred, okay? Then we can define the conditional PDF of X given event A. Right, and it's defined as follows: f of x given A, so that's the notation, has two parts. It's basically f of x divided by probability of A when x belongs to A and 0 otherwise. Now, since someone told us that x is already in A, that means you have to trust that someone. So if x is not in A, that is the else part, all right, that density takes on the value exactly 0. But if x is in A, it has the same shape as the original probability density function, except that there's this other scaling factor. What is the point of the scaling factor here? What is the point of probability of A? It is to make this, anyone has any, conditional? Yes, it is to make it conditional, but every conditional PDF is a bona fide PDF. Yes, Alvin Chi is right. Make the area become 1. Thank you very much. So just a small remark. The normalization by probability of A is to ensure that the integral of f given A x dx is equal to 1. And we can actually calculate this, okay? So the integral of minus infinity to infinity of f of x given x dx. Now, this guy here is only non-zero when x is in a, so we can integrate over a only. Fx given ax, fx given a of x dx. But by the definition on a, right, this is fxx divided by probability of a dx. So this becomes, you can bring out the 1 over probability of a, and that is where we need the probability of the event a to be positive. Otherwise, we are dividing by 0, which is not allowed in math. All right, so then we can integrate this as per normal over a, all right, dx. But this guy here now is exactly the probability of a, because we are integrating the density over a, that is probability of a. And because the probability of a is positive, so we can cancel. If it is 0, we cannot cancel. That is a rule of math. So this is 1. So the conditional density is a legitimate probability density function. Okay, so here what we mean is that on a, f of x given a and f of x have the same shape, except that the conditional version is taller. Shape. Okay. So that is that. Actually, we have already done this. Okay. So I want to illustrate this using a particular example. Last time we illustrated it using a very simple example. So now let us consider a slightly more interesting but involved example, and that is the exponential distribution. Okay, so this example illustrates what is called the memoryless property of the exponential. Memoryless property of the exponential PDF. So this is something that I teach in great detail. Actually, I'm also teaching another class right now. It's the EE2012A. We talk about this in great detail. All right. But here, this is a simplified version for your interest. So you have a certain random variable t that is exponential lambda. That means that its probability density function looks like this. Lambda e to the minus lambda t for t bigger than or equal to 0, and otherwise it's 0. Okay, so the density looks like this. Density is a short form of saying probability density function. Okay, otherwise too long-winded. Okay, so we have this. So this is ft of t, and t is here, and the density looks like this. It's 0 on the left-hand side, exactly, and it's exponentially decaying on the positive side. I don't mean this. Not nice. Okay, so this part here is lambda. Okay, so we have this particular density. All right, and this represents the amount of time you have to wait for a bus. So you go down to the bus and you want to take the 95 to the MRT station. All right, so this distribution here, this random variable is actually a good model for your waiting time for the 95. Okay, now you are being told by someone that the event A occurred. So A is equal to the event that t is bigger than or equal to t. It's bigger than t, where t is some positive number. So what does this mean? You actually walk down to the bus stop, okay, and say t is 5 minutes. And you have already waited for 5 minutes and the bus did not come. So t bigger than t, say t is 5 minutes. So the bus actually took more than 5 minutes to arrive. That is the meaning of this event, right? Because the waiting time is bigger than 5 minutes, and you have already waited there for 5 minutes, okay? You've done nothing. And now I'm asking the question, all right? Let's now x be a new random variable that represents the additional waiting time until the bus 95 comes. So this event means it's if and only if the bus 95 has not come after t minutes. So this is this event here. Okay. So let x be the additional waiting. You've already waited 5 minutes, right? Or t minutes. Now, how long more? What is the distribution of the amount of additional time you have to wait until the bus comes? All right. This is very surprising if we assume this density. I'm going to show you something very surprising. Okay. So the probability density function that we want to derive is that of x. But in order to get to x, I want to show you some other calculation. Let's consider probability that x is bigger than x, given that the bus took more than 5 minutes to arrive, which is the event A. Okay, understand? Once we have this, then we can derive the cumulative distribution function. The cumulative is this direction. This one is the so-called complementary CDF, the other way. But it turns out that the other way is quite useful for us to get the real CDF. Okay, so this is nothing but probability that the total time is bigger than t plus x, given this is t greater than t. So the picture is as follows. Okay, now this is when you came into the bus stop at time 0. Now here, bus has not arrived, and this is x, the additional waiting time. Okay, so basically I'm doing this calculation and I'm trying to understand the probability density function of the additional waiting time. Okay, so if the additional waiting time is bigger than x, that means that the total waiting time is bigger than t plus x, right? T plus this additional part, right? So now let's do it. So this naturally calls for Bayes' rule, t greater than t plus x and t bigger than t, divided by probability t bigger than t. Okay, so this is nothing but Bayes' rule, and let me remove this a little. Now, what can you tell me about the top? So x and t are both positive numbers. If the random variable t is bigger than t plus x and it is bigger than t, can we simplify the numerator? So we have a certain number that is bigger than t plus x, and we have a certain the same number is bigger than t. What can we say? Can we simplify this, Alvin G? I think we can. If a number is bigger than 6 and a number is bigger than 4, the number, oh, Alvin G does not understand. Okay, so let's say this number is 6. It is bigger than 4, and at the same time, it is bigger than a smaller number 3. Say t is 3 and x is 1. Okay, then is this piece of information that the number is bigger than 3 relevant? It's completely useless, right? Because I know that it's bigger than a number that is 4. Right, Alvin Chi, you understand now? So the point I want to make is that after I remove all this, that this whole expression here can be significantly simplified to the following. I can just get rid of this. It's not important. All right, basically, I can get rid of it because there is one event that is dominant. You understand? The other one is not important. Because if you are bigger than t plus x, you are definitely bigger than t. Everything is positive. Get the point? So now we know that t is an exponential random variable. So this is the this is something that we can compute. Exponential random variable bigger than something. And it turns out that you can rewrite the exponential random variable bigger than something, okay, as e to the minus lambda t plus x divided by e to the minus lambda t. That is the probability that an exponential random variable is bigger than something. This can be computed. Maybe I'll do the computation later. Okay, maybe I'll do it here. So the probability that an exponential random variable is bigger than s is integrate from s to infinity lambda e to the minus lambda t dt. So we can do this integration minus how many? Lambda t. You put in infinity and s, so this becomes e to the minus lambda s. So you can put s equals to t plus x, and t, you can get this. Okay, so but this can be simplified because of the exponential property. This is e to the minus lambda x. Okay, So this is the complementary CDF. This is the probability that x is bigger than x given A is equal to e to the minus lambda x. This implies that the CDF, which is the probability that x is smaller than x, we need to go this direction, is equal to 1 minus e to the minus lambda x. Okay, but if you differentiate this to get the PDF, then what you get is lambda e to the minus lambda x. Okay, I have to be careful here. This is for the interesting range only, x bigger than 0. Here is x bigger than 0, 0 otherwise. Okay, so what happens here is that the conclusion is that the conditional CDF of x is the same, is exponential with parameter lambda, regardless of the time t that has elapsed. So this is very interesting. Why? Because my story is as follows. Okay, you go to the bus stop and then you wait there for 5 minutes and the bus did not arrive. The expected amount of time, additional amount of time that you have to wait for the bus to arrive is the same as when you stepped into the bus stop. This is a bit unbelievable, actually, because, right, buses are usually regular, right? Every 15 minutes they will come. So a process in which the buses come regularly does not satisfy this exponential property. Because this exponential property says that, okay, if a bus did not come for 5 minutes, the amount of additional waiting time you need to wait is the same as at the very beginning, if we assume this model. So one can question whether this model is useful or not. All right, so I want to draw a picture to illustrate this fact here. So this is the original density. Okay, this is the original probability density function of t. So this is the amount, this represents the amount of time you have to wait once you step into the bus stop. But suppose, right, you have already stepped into there and no bus arrived up to time 5 minutes. Now, the additional waiting time you have to wait, right, is given by this particular density. It has the exact same shape, it's only shifted. So this density is given, is exactly f of t given a t, all right? So here A is the event that the waiting time is bigger than t. And this has the shape lambda e to the minus lambda, this is e, this is s here, otherwise something is wrong. S minus t for s bigger than or equal to t, and s less than t else a 0. All right, because we know for sure that our waiting time is more than 5 minutes, say t is 5 minutes. So basically the whole density shifts to the right. There is no change at all in the shape if we assume the exponential model. Okay, this is unrealistic in practice because buses usually come at regular intervals. But this is actually a very good model for the arrival of football goals, as I mentioned before. I don't know whether you remember or not. This is a very good model. If you have watched a football game for 20 minutes and there is no goal scored, then the expected amount of time you have to wait until the next goal is scored is as if it's at the start of the game. Actually, it's not quite true. So if you know football, most of the goals are scored after the 90th minute. All right, so there's a concentration towards the back end, but we won't worry about those. Okay, so here is a particular example that we can see conditioning in place for the exponential distribution. All right, we have this memoryless property. Okay, any questions on this calculation? Does anyone have any questions on the calculation? So if you're interested in this, you can take my graduate probability class. Yeah, I teach this, and we are going to have a quiz tomorrow. I teach graduate probability tomorrow. All right, so the point here is that these have the same shape. In my graduate probability class, I have a few undergrads, EE undergrads. They are usually the top students in my graduate probability class. I taught that class for many years already. All right, anyway, so we have an analog of the law of total probability. Okay, so if we have events A1, A2, all the way up to AN, they are disjoint events satisfying the condition that each event has positive probability. Then we can say a lot of things, all right? Then the PDF of X can be decomposed into the probability of this individual event and the conditional PDF of each one, where the conditional PDF is defined as above. Okay, so this is f of x given AI is the conditional PDF that is defined as f of x divided by probability of AI when x belongs to AI and 0 otherwise. So this is a direct generalization of the above. Okay, so now I basically split the sample space into various parts, and to each part there's a certain probability, and then I multiply that probability with the corresponding conditional PDF and sum it up. Okay, so this is just a fact. In a book, they provide a proof, but I'm not going to do it. I'm not going to do a proof here because here we're not in the business of proving things. If you take my graduate probability class, then you should know how to prove everything. Okay, so we want to use this result to answer some interesting questions. All right, the next example I'm going to do illustrates how to use this formula, and it illustrates how to use this formula in a pretty interesting manner and not obvious. Okay, so here's the example. Okay, so you have an MRT train that arrives to Kentridge Station every quarter. This is an American book. They like to use quarter. Every quarter hour starting from 6 a.m. Okay, but you arrive at the Kentridge Station, you arrive uniformly between 7:10 a.m. and 7:30 a.m. Okay, so the question is, can you find the PDF of your waiting time of the first PDF of the time to the first arrival of the train? So how much time do you have to wait on the platform? Okay, you see that this question is a little bit complicated because the trains arrive at 6, quarter past, half past, a quarter to, and on the hour. So that means 6 o'clock, 6:15, 6:30, 6:45, and 7 o'clock, and 7:15 and 7:30. All right, but you arrive at this strange interval, not quite at quarter past, not quite on the hour. Right? So there's some discrepancy. So there's some calculation to be done, right? So 7:10, oh well, if you arrive at 7:10, then your waiting time is uniformly distributed between 0 and 5 minutes. Because the next train will deterministically come at 7:15. All right? If you arrive at 7:16, however, then what happens? Something else happens. So there are several cases here. Can you see? Not so easy. All right, so let's do this systematically. All right, so let us just sketch a few things. All right, let X be arrival time. Okay, so X has this particular PDF. All right, the PDF is in terms of units of minutes, so time, and this is fx of x. So 7, 10, and 7:30. So I think it's easy to see that this guy here is 1/20. All right, if we measure in terms of minutes. So that's your PDF of when you arrive. Cool. So it makes sense, right? If you think about it, if Oliver, you think about it, it makes sense for us to split this into two parts. where this part here is 7:15, a beautiful number here. Because, right, the trains come at 7, 7:15, and 7:30. So it makes sense to split the analysis into two parts, before 7:15 and after 7:15. So we're going to call this event A and this event B. Specifically, we are going to write down A is the event that we arrive between 7 and 7:15. Now, and this is exactly the event that I board the quarter past train. Okay. Now, the other complementary event, if you don't arrive in this interval, then you are arriving late. Okay, so you arrive after the quarter, and then you are boarding the half-past train. You board the 7:30 train. You agree? Logical, right? So, Vanessa, you agree, right? There are only two cases. Either you come early or you come late. All right. So now we need to deduce. All right. We need to deduce some things. The conditional PDF, because what is our goal? Our goal is to use the formula given by the following: f of x given ax, probability of A, plus f of x given bx, probability of B. Because A, B form a partition of the sample space, so we want to use this formula here. Okay, A and B form a partition of the sample space. There are only two objects here. All right, and I want to use this formula, and that's our objective. So we need to figure out all these numbers. All right, so condition on the event A. Condition on event A. What is the distribution? What is the waiting time? Okay, and here we have condition on event B. Let's draw the probability density function of our waiting times. Okay. Condition on the event A, our waiting time is given, the time that we bought, rather the waiting time is given by the following. So 7, 10, all the way to 7:15, uniform. That is when I will board. Okay. Right, so it's uniform, and this must be 1/5. So that's f of x given ax. Okay. Right. So there's condition on event A, but if we condition on event B, all right, then what we have is the following. We start at 7:15 and we go all the way up to 7:30. Right. So that is going to be uniform on here. That is when I arrive, condition that I arrive after 7:15. So this is going to be 1/15. As I said, right? Suppose I know that I arrive early, then the shape of the probability density function is the same, except that we must rescale to make sure that this adds up to 1 or integrates to 1. Now, condition, however, on event B, I know that I'm on this side. However, I need to rescale this from 1/20 to 1/15 to make sure that this integrates to 1. This is 15 minutes. I need to multiply 1/15 to make sure that this area here is 1. Make sense? Okay, so we have condition on A and B. All right, now what we are going to do is to let y be our waiting time. That is what we are interested in. So let's draw the PDF of y. Now, conditioned on the fact that we are arriving early, f of y given A, our waiting time is anything between 0 to 5 minutes, uniform. That is our waiting time under the A event. Y is the waiting time. X is your arrival time. Now, Y is your waiting time. If you arrive early, you wait anywhere between 0 to 5 minutes, uniformly at random. However, if you arrive late, you could wait a little bit longer. And if you arrive, you're unlucky, you arrive at 7:15 plus epsilon. That means slightly after 7:15. Then you are going to wait 50 minutes. Okay, so the point I want to try and make is that under the alternative, that means you wait, you arrive late, then you have to wait anywhere from 0 to 15 minutes. Do you agree? Cool, right? Very clear, right? So now we want to figure out the probability density function of y. Okay, sorry, I said here x, right? But really I want y. But the rule that I'm using is the same. Huh? Y. I'm interested in this. Okay, so basically I just have to calculate this formula, but it's also not so easy to calculate. All right, so we have to be a bit systematic. So in my math class, I used to say that we have to do good bookkeeping. You need to keep your books in the right order. All right, so let's see. Now, in the case y is between 0 and 5, what is this number? All right, what is the probability of A first? So A is this particular event. What is the chance that it will arrive early? Let me ask some random people like Alvin G. So A is this event here. What is the probability you arrive early? Because I know that Alvin G will reply to me. Alvin G, what's the probability of A? Look at the picture. Okay, anyone wants to help Alvin G? 1/4, yes. Very good. So this has two cases. We'll do this systematically. So this is 1/4. And of course, probability of B will be 3/4. Okay, fine. What is f of y given A of y when y is between 0 and 5? Let's see. So if you are here, right? So the probability density function takes on the value 1/5 because we are anywhere from here to here. So that's 1/5. Okay. Now, what is the probability density function of y condition on B when y is between 0 and 5? So we are here. We are somewhere here. Okay. But if you're somewhere here, you look up, oh, the value is 115. All right. So we are 115 here. Okay. All right. So let's do the other case. So here y is now between 20 and 15. Oh, sorry. It's between here 15 and 5. Okay. So now the probability of A stays the same. The probability of B stays the same. What is f of y given A when y is between 5 and 15? Right. Very good. Someone said 0 in the hall here. Good. Now, what is f of y given by when y is in this interval? Now we are looking here. 1/15, right? Because I'm looking here. So this particular number, I got by looking here, and I look it upwards here. That's 1/15. Got it? Thank you very much. People are with me. Cool. You are with me. Very good. So now, did I make any mistake now? Did I make any mistake? Now correct. Okay. Then Oliver disturb me. Okay. Thank you very much. So it is 1/4 because if I look at this original probability density function, what is the probability of A? Well, it is 5. This is uniform. It is 5 minutes out of 20 minutes. 5 out of 20 is 1/4. You look at this, you only have 1/4 of the cake to eat, right? Only a little bit of cake to eat. The other friends there have 3/4 of the cake to eat. All right, so that is 1/4 because this is 5 minutes only. Okay, cool. So now we can clear all these fractions to make this look nice. All right, and I'm not going to do the math here. This 1/10, 1/20, and 5 to 15, and 0 y 5. So this looks like this. Your waiting time looks like this. All right. There's a very high chance that you wait 5 minutes. 5 minutes is 1/10, 5, and this is 10. This is 15, and there's a chance that you wait up to 15 minutes, but the chance here is kind of uniform, 1/20. This is FYY. And the good students, after they derive this, will ask what question? But how to check this? Does this integrate to 1? Okay. Now, this indeed integrates to 1 because let's look at this area here. It's 5 times, so this area is 5 times 1/10, which is half. And this area over here is 10 times 1/20, which is also half. So half plus half equals 1. So my numbers are all correct. Got it? Understood? So that's a way for us to use conditioning on events. Now this example is not so easy, but it actually illustrates a point. All right, and I hope that I explained it reasonably okay. Any questions on this example? So here in this class, we don't need to do too many proofs, but here we need to know how to use the formula, right? Use the formula properly. And some of these examples are kind of deep. So in my graduate class, I spent actually 9 hours talking about this thing. Yeah. But my graduate class, if you're interested, you don't need to take my graduate class on probability after this semester, because my graduate class, all the lectures are on YouTube. Yeah, if you're interested to continue studying this. Okay, yep. So now we have talked about conditioning of a particular random variable on an event. We can now talk about conditioning of a random variable on another random variable. So that again is kind of a tricky concept. Conditioning of a continuous random variable on another continuous random variable. Actually, this is a difficult concept if we want to do it properly. Okay, so the conditional PDF, we are given 2 random variables, okay, 2 continuous random variables. The conditional PDF of one of them, of x, given the event y is equal to y, is defined by fx of fx given y, x given y, is given by this. These 2 objects on the right hand side are well defined, the joint PDF and the marginal PDF. We need to have the caveat that this is positive, otherwise nothing makes sense. We cannot divide by 0. Okay, this is very similar to base rule, and it's also very similar to the discrete case where all the f's are replaced by p, the PMF. Here we just change the notation from p to f because we are in the continuous land. All right, so this is the conditional PDF of a random variable given another random variable, x given y. All right, now notice that this is a bit different from this sort of notation here because I don't have given something here. Because here I'm already conditioning on an event. There's no need to talk about what that event value takes on. All right, so this is a different object from this because here there's a conditioning that this random variable takes on this value. All right, so conditioning of a random variable on an event versus conditioning or a random variable on another random variable is very different. Okay, so we can actually rewrite this in a slightly different way. Okay, we can rewrite this in a slightly different way. Why? Okay, so before that, let me just remark the following. Okay, given any y such that fy of y is positive, then the conditional PDF is a legitimate PDF. So if I just look at this particular function as a function of x, y is fixed, then this has all the properties of a PDF. Why is that so? Number 1, fx given y, x given y is always non-negative, as is required for every PDF. Okay, this is for all. This is a math thing. For all x. All right. And number 2, what is the second defining property of a usual PDF? It must integrate to 1, right? So does this integrate to 1? Okay, so let's check. I don't know whether it does or not. Okay, so let's check that this integrates to 1. dx for every fixed y. Okay, so we have to then put in the the definition fy y dx. I'm not going to put in the let's say put in the limits here, but fy is a constant, and now we integrate this way. So constants with respect to x can be brought outside. But now at this point in time, you notice that this integral yields exactly fyy by the marginalization property that we talked about 1 or 2 lectures ago. Now at this point, is this equal to 1? Yes. Why? Math people will have to say one more sentence. Because these two objects here are not equal to 0. If they are, you cannot cancel. Things can go terribly wrong. Okay, so this is so if I just fix y and I look at this, I look at x, this is a usual PDF. Okay, so all this sounds very abstract. So again, we need to resort to some examples to help us understand this concept. All right, so let me not draw any new material because now my drawing is very bad. So let me just use this example that we had painstakingly derived 2 lectures ago. You remember this picture? Whether or not you remember, it doesn't matter because now I'm going to talk about it again. Okay, so let's see. Okay, so let's look at this particular example. Move this down. Okay. So let's look at one example to illustrate a point. So this is 1/4, right? Because the area of S is 4. Right? So now, if I know, so Oliver told me that in this particular random experiment in which I drew an X and a Y, Oliver told me that he observed that Y is 1.5. Okay? So in particular, if Y is equal to 1.5, then can I figure out what is the conditional probability density function of X given that Y is 1.5? Okay? So how do I do this, right? So actually, when I run this experiment and I observe X and Y, Oliver told me that he actually saw that Y is exactly 1.5. So we are here, 1.5, and I draw a line here because I know that I must be somewhere on this line. I must be somewhere on this line. So now I'm trying to find how X is distributed, conditioned on the fact that I know Y is 1.5. So can X be over on this side? Cannot, there's no mass here. Can X be over here? Cannot, because there's no mass over here. Can X be here? Cannot, because Oliver gave me side information that Y is 1.5, so it cannot be here. So the only non-zero part that X can take on is between 1 and 2. All right, then how is it distributed? All right, so let's draw the PDF of f of x given y, x given that y is 1.5. All right, so let's draw a nice picture here. Right, so 1, 2, 3 are the critical points. But if I look this way and I look only at this part here, that's where y is 1.5. I see that x can only take on values from 1 to 2. All right, so it's here. Uniform. And what does this height have to be? This height must necessarily be 1 for this to be a legitimate PDF. 1. Understood? Because I'm looking in this direction. All right, but however, if Oliver or Vanessa told me something else, all right, let's say this one here, let's say something else, okay. If, however, someone else told me that y is 2.3, okay, what is the density of f of x given y when y is 2.3? Well, it's no longer this picture here, but something else. Okay, so where are we now? Well, if I look at this picture, okay, so someone told me that it's 2.3, we are here. I am now living in this world where y is 2.3. I'm living on this line here, the green line. Okay, now then you ask yourself, can x take on any values less than 1? No. Can x take on any value greater than 3? No. but x can take on values from 1 to 3. Perfectly legitimate. All right. So the answer is uniformly distributed between 1 to 3. Like this. And what is this height here? It has necessarily got to be, Sean. Very good. Oh, Sean's brain moves faster than me. So do you get the picture? Do you get the understanding here? So when someone tells us that y is 2.3, we are restricting ourselves to that universe, this universe only. Then we are asking ourselves, well, where can x live? All right, x, all this is uniform. So x can live between 1 to 3. It must be uniform here. But later on, we'll see some more exciting things. Everyone understand? Now you can continue to play with this, but I'm not going to do it. All right, so this is the concept of conditioning of a random variable on another random variable, taking on certain values. Super important. If you continue in your undergraduate education to do 3731, I don't know whether people do that or not, or 3131, the communications one. In communications, you all have to deal with probabilities, right? So you need to have good foundation in all these things. Or some other things like, I don't know. I don't teach in this department too much. So let's consider another example. All right. Let's consider this. Okay. All the examples go from easy to difficult. This is the circular uniform example. Today in my tutorial, we have done some circular things. Okay. So now we have a particular joint probability, then joint random variables, jointly continuous random variables, and these are uniformly distributed in a circle centered at the origin with radius r. Okay, so the equation for that, I don't know whether you remember or not, but it's not so important as of now. I can remind you. So the idea is the following. Okay, so you have this particular picture here. X and Y are uniformly distributed in this region here. So here. So it's like you throw a dart at the dartboard, and you are equally likely to land in a region that is distance r from the origin. Okay, and you are uniform within this region here, and you are so good that you don't throw outside. Okay, so you're not like me where you can actually throw here. Okay, no, that's not allowed. All right. So what is the probability density function if fxy, x comma y is equal to 1 over pi r squared, because the area of this green circle is pi r squared, when x and y belong to the circle and 0 otherwise. Okay, and this circle C is a set of all xy pairs such that x squared plus y squared is less than r squared. This is the equation of a circle. I don't know whether you recall. Okay, so now we would like to find the conditional probability density function of x given y. Now this is symmetric in x and y, so it doesn't really matter what we condition on. If we can do something, if we can do condition on y, we can also do condition on x. All right. So we want to calculate, our objective now is to calculate the conditional PDF. This is a bit difficult, okay? PDF or f of x given y, x given y. All right. All right. Now, this can be split into a few cases, all right? Case 1, the absolute value of y is bigger than r. So someone told me now, all right? So now this is something that Oliver told us or something, right? Just now Oliver told us in the previous picture that y is equal to 2.3 or 1.5. Now Oliver told us that y is bigger than r. Is this believable? No, because our skill is so good that we will definitely hit the dart inside the green region. So in this particular case, the conditional density is equal to 0. There's no chance of x taking any value, reasonable value, when y is outside the range. So this part here is represented as, oh, y is here. Oh, sorry, y is here. Gosh, y is here. Not allowed, right? Because we are only allowing values that are inside the circle. So it's not allowed. All right. So the case 2 is the interesting case. All right. When y, absolute value of y, is less than or equal to r. That means that, okay, Oliver told us something reasonable. All right, we are here somewhere or here. Okay. So we are going to do this generically. We are not going to focus on particular values, numerical values of y. We're going to do it for a general y. Okay. So let's try to figure out, our objective is to figure out the conditional density. But the way we are going to get to this endpoint, this finishing line, is to use Bayes' formula, which is the following. Okay, so we have the above. We have the numerator, because the numerator is given here. But the problem is we don't have the denominator. So in order for us to get to the conditional, we should try to figure out the denominator here. Then we can plug it into this formula, and then we are all set and done, and we can go home. Okay, so now let's try to figure out the denominator, which is the f of y of y. All right. So in order to do that, we integrate out x. So I do not know whether David Woodside is here, because he was confused last time whether he should integrate out x or y. So let me put this on record, since this is recorded, right? If you are interested in y, we take out x. Then there's no more x to talk about. Understand? So David, please do not be confused. Then we integrate from here to there. All right. But now all the action of x only happens from from over the region x squared plus y squared less than r squared. This is the set of x's that we have probability mass. So what are we trying to do here? Okay, let me draw a picture. Now, someone told us that y is equal to y. So here, someone told us, okay, that is a special value of y. So we need to integrate from this point here to that point there. Okay, and what is this point and that point? This point here is exactly minus square root r squared minus y squared by Pythagoras theorem, if you wish. This point here is in r squared minus y squared. Okay, this is by Pythagoras theorem. I don't know whether you remember or not. Okay, so we can do the following. You integrate from minus square root r squared minus y squared to square root r squared minus y squared. Right, because, okay, one more time, we are fixing a value of y, and we are looking at all possible values of x that are admissible, that lead to the density being positive. Then we need to integrate from this point all the way to this point. Okay, but given this particular equation, if I know y is equal to y, all right, x squared is equal to r squared minus y squared. So x is equal to plus minus square root r squared minus y squared, to do it slowly. Understand? So this point is plus r squared minus y squared. This is minus r squared minus y squared. Okay, so those are my limits of integration, and the inside here is 1 over pi r squared dx. So now this is easy. This becomes 2 square root r squared minus y squared divided by pi r squared. So that is my marginal density for all y less than or equal to r. Okay, any questions? This is a little bit involved, sorry, but since we are in university, we must do things that are a bit involved. All right, so we fix y equals to y, and we are looking at where are the limits of integration. The limits of integration are precisely those values of x that result in a change of the density, change from 0 to something positive, and it happens right here and right there. But by solving some simple equation, we get that the left endpoint is this, the right endpoint is this, and so we can plug in this and that to the limits here. And this guy does not depend on x, so it's just this constant multiplied by the difference between these two. And the difference between these two is 2 times of each one of them. Okay, so we have the marginal density of y And it looks like that. It looks like that. Okay, so between R and minus R, that is the marginal density or marginal PDF, Fy of y. Okay. This is not very symmetric. It should be symmetric. Okay. All right. So that is that density. Okay. And 0 elsewhere. Okay. So remember that our objective is the conditional PDF, and the conditional PDF looks like this. Conditional PDF, f of x given y, x given y. And we desire to use the formula joint divided by marginal. And we have painstakingly figured out the marginal. So the joint is 1 over pi r squared from above. The marginal is exactly this guy here. So yeah, we can put it here. All right. And now we see some beautiful cancellation of this and that. And now we see that this can be simplified to 1 over 2 square root r squared minus y squared. And actually, the point that this question is trying to make here is that, all right, this is true if x squared plus y squared is less than r squared. Now, the point here is that f of x given y is uniform, is uniformly distributed. All right, is uniformly distributed here. Okay, the reason is because this guy here does not depend on x. All right, does not depend on x at all, so it is uniformly distributed. Now, let me try to draw another picture. So let me bring this picture down to fully illustrate this fact here. So someone told us, when I want to evaluate this guy, the probability density function of x given y, what is happening is that I am looking at a particular slice. Just like for that rectangular example, I'm looking at a particular slice. Now I'm living on this slice. What is the vision that I have about x? Now, all these points are uniformly distributed. So clearly x should be uniformly distributed. But what is the range of values of x? Well, it's between this point and that point. Okay, and what we have painstakingly derived here, okay, is the following probability density function of x condition that y is equal to y. So here is f of x given y, x given y. Okay, so the left endpoint here is minus square root r squared minus y squared, and the right endpoint here is r squared minus y squared. And and what is the height? Is uniform. So what is the height? The height here, in order to make this a legitimate probability density function, is 1 over 2 square root r squared minus y squared. Okay, which is exactly this value here. So the reason why I have to have this constant here is because I want what? I want the area under this graph, the area here must be equal to 1, because the conditional PDF is a legitimate PDF, and so its area must be 1. So the area here is equal to 1. So as you can see here, if someone tell me y equals to y, we cut here, and then we look at this segment here. This segment here is exactly this segment here, from minus this to plus this. Is that clear? So we have the algebraic way of doing things using algebra, and we just have to visualize this. We have the visual way of doing things as well. Does anyone have any questions here? Let me call on random people. Alvin G, I know Alvin G. Any questions? Is this very clear? So this line here happens to be corresponding to this line here. Okay. Is this clear? Everyone in this audience, is this clear? Take a break. All right, we'll take a break until 3:10. All right, and I will stop this recording So after the quiz, right? After the quiz next Tuesday, we have this, we still have lectures, but in one of those lectures leading up to the final, right? I'm asking one of my students to do it because she wants to be a professor. So hopefully you don't mind me disappearing and she take over. I'll be here to make sure that she doesn't say the wrong things, but let's give her a try. Okay? She's pretty good. She has taught my graduate class before in probability. So I think she should be okay. Let's give her a chance. Right, let me consider another example because I think we do have time. So let me consider this particular example. All right, so the speed of a vehicle x, okay, is exponential with mean 50 miles per hour. All right, this book is very Americanized, okay? So now there is a police radar that is picking up the speed of the car. Police radar measurement y of vehicle speed, right, has, however, an error that is Gaussian. You remember Gaussian random variables? Yeah, the most common. With zero mean and standard deviation 10% of x. All right. So now we would like to try to find the joint probability density function of x and y. This sounds a bit challenging. All right. There are a lot of things happening here at the same time. All right. So let's do it step by step. So we want the probability density function of x and y. So we need to try to pass all this English into some math, right? So we know for sure that x is easy. The probability density function of x is an exponential random variable with mean 50 miles per hour. So the mean of the exponential random variable is equal to 50, but for an exponential random variable, the mean is 1 over lambda. Okay, where lambda is the parameter of the exponential random variable. That means that lambda is 1 over 50. Lambda is called the rate of the exponential random variable if you wish. So the PDF of x is 1 over 50, e to the minus 1 over 50 x for x non-negative and x less than 0, this is 0. So that is the PDF of x. But we want the PDF of x and y, right? So we have a lot more work to do. Okay, so what we do know is that given that the speed of the car is x, the police measurement of the vehicle speed is a Gaussian random variable with 0 mean, okay? And the standard deviation is 10% of x. All right, the error is 0 mean and it has a standard deviation 10% of x. So what is the probability density function of y given x? Well, this is Gaussian with mean of x and standard deviation x over 10. Okay, so if I fix x and I just look at y, then the police measurement of my speed is centered at x, but it has a standard deviation that depends on my speed. Okay, why is that so? Because the faster you drive, right, the more error there is in the measurement of the police measurement. This is called in statistics heteroscedatic. All right, basically, for example, the taller you are, the more error you have in assessing things around you because you are farther away. All right, so the shorter you are, then the easier it is for you to pinpoint the height of a particular object because you are closer. All right, so the faster you drive, the more error, the more variation the police measurement has. Okay, but so this is some This is believable. This in statistics is called heteroscedasticity, and there's a lot of things we can do about it and say about it. All right. So what is this density? All right. So for a Gaussian with mean mu and variance sigma squared, so that is mu sigma squared. Then the density is given by the following: 1 over square root 2 pi sigma e to the minus z minus mu squared over 2 sigma squared. Okay, so that is the normal density. Okay, so now here this is slightly different because the parameters are different. 1 over square root 2 pi. The standard, put down the standard deviation is this. Now we have y minus the mean quantity squared divided by 2 of the variance. The variance is the standard deviation quantity squared. This looks a bit difficult and a lot of things happening, but well, this is just a way to interpret the question. All right. So now the joint density is given by fxy. Xy is the marginal multiplied by the conditional. This is the formula. Because above I told you that the conditional is the joint divided by the marginal. So we can just rearrange things. And after we are all said and done, this is 1 over 50 e to the minus 1 over 50 x. And this is 10 over square root 2 pi x. And here we have e to the minus 50 y minus x squared over x squared. Now here x is constrained to be non-negative and y can be anything. Right? So y can take on all real numbers. That is what y in R means. Okay, because I mean, if you travel at a very slow speed, then well, the measurement device can be very bad to actually give you a negative speed. So y can actually be negative. All right, so here, this example basically illustrates how to use this formula. Okay, first we figure out the density of x. Then based on x, we try to understand the story. The measurement error has 0 mean. So the real measurement has mean exactly x. The measurement error has standard deviation x over 10. So the actual measurement also has standard deviation x over 10. Okay. Now, then you plug into this formula, the standard deviation. Here you must plug the variance. And then the mean is here, the variance is here, the standard deviation is here. Then you readjust everything to make it look nice. Okay. So this is just some illustration of how to use the formula. Any questions? Right. So now I want to talk about one last concept, which is the conditional expectation. Actually, two last concepts, but the independence part is easy. So I want to talk about conditional expectation and do one example, and then just end off with condition and end off with independence. Okay. So we have done conditional expectation on many occasions. So this is one more occasion. So here is the topic of conditional expectation. So here we have xy, a pair of jointly continuous random variables. All right. And A is some event with the probability of A being bigger than 0. Then we can define the conditional expectation of x given event A in the following way. Let me say this is given event A to drive home the point. Well, that is given a notation x given event A. Well, that is the same as, that's defined to be minus infinity to infinity. You integrate with respect to the conditional PDF. So here we integrate with respect to the conditional. So this is the conditional PDF of x given event A. All right. So that is the definition. We will see how to use it in a jiffy. Now, we can also talk about a conditional expectation given that a random variable y takes on the little value y. Okay. Now, then this has to be readjusted a little bit, but not too much. y equals to y is equal to this, y x given y. Okay, so we can always talk about conditioning on events. We can also talk about conditioning on random variables. If you want to study this sort of things a little bit more, we can talk about conditioning on sigma algebras also. That's the most fundamental. Okay, but for simplicity, there are only two conditionings that you need to internalize. All right. So we can also talk about the expected value rule. This afternoon in the tutorial, we did look at expected value rule. Okay, given an event. So sometimes we are interested to compute the expectation value of some function of x conditioned on some event. So we are bringing in several concepts now. In the tutorial, we actually painstakingly derived the probability mass function of this guy, and then found the expected value of this using the standard formula for expectation. But we don't have to do that. We just have to put g of x here, f of x given a x dx. Okay, so you can also talk about the expected value rule given a particular random variable. Okay, so above was the expected value rule given an event A. Here we are given that random variable y takes on value little y. So all this is very repetitive, I know, sorry about that, but we have to get through this. The x here. Here we are conditioning on A, but on the special event, y equals to y. We can do this as well. All right. And we also can talk about the total expectation theorem in this context. All right. And we'll see how to use this. As I mentioned, we need to know how to use this. We have a bunch of disjoint events, A1, A2, all the way up to A. And they are disjoint events that form a partition of the sample space. Partition of the sample space omega. That means that AI intersect AJ is empty for I not equal to J. And if you take the union, you recover the entire sample space. The picture is like you have this sample space here, omega, and you can cut it up into several parts, A1, A2, A3, A4, A5. They don't overlap with each other, and together they form the entire universe. All right. So now in this case here, the total expectation theorem can be written as follows. I'm interested in the expectation value of x, but I know the individual expectations. So I can use a divide and conquer approach to find the summons first, to find what I'm summing over all these things first, then I sum it up. Okay. So that's the total expectation theorem. Okay. So now let me do a particular example, right, to illustrate all these concepts. Right. So now X has the following piecewise constant PDF. Right. So it has a PDF given by the following fx of x, x, 1 and 2. So this is 1/3. And this is 2/3. So the first thing that we should check when I tell you that this is a PDF is what? The area underneath must be 1. And indeed it's 1 because this area here is 1/3 and this area over here is 2/3. So it adds up to 1. So all the numbers are correct. Okay. We also know, all right, let's just define some events. Event A1 is the event that X lands between 0 and 1. And event A2 is the event that X lands between 1 and 2. All right, so these are two disjoint events that span the entire sample space. Because the union of A1, A2 is a set of all possible X's that X can possibly take on. All right, so it's also clear that P of A1 is equal to 1/3 and P of A2 is equal to 2/3. And the reason for this is because the area under here is 1/3 And the area under there is, of course, 2/3. Okay, so we have this nice areas here. This is 2/3 and this 1/3. So now what I would like to do is I would like to figure out the expectation value of x. So our goal is to find the expectation value of x. Of course, even before I tell you about all this conditioning business, right? You can just go ahead to integrate these sort of things. But it's very painful. We never like brute force integration, or at least I don't like. We like elegance. And what I'm going to show you is very elegant. We don't need to do too much work. Okay? So let us see. What is the expected value? So I'm interested in the expectation and the variance of x. We can use long-winded methods to calculate this, but I'm going to calculate this to you in a very fast way. Okay? So suppose, right, someone told us that A1 occurred. That means that x is between 0 and 1. Someone told us that. What is the expectation value of x? Okay, so this one tells us that, okay, x is between 0 and 1. We are here. What is the expectation value of x? Very good. Someone gave me half. Superb. Now, A2. What is the expectation of x when I know that I'm in the right interval? Come on. 3/2. Thank you. Now, these are all Wicket's intuition. But can we actually use the formula to actually figure this out? Okay, now I'm going to do one of them. Expected value of x given A1 is what integral of fx given A1x dx from 0 to 1. Okay, actually from minus infinity to infinity. I like to do things slowly for you. That's the vanilla formula. But what is f of x given A1? Well, I know because Oliver told me that I'm in A1. So my x can only range from 0 to 1. Okay, so I know that my x is uniform on 0 to 1. Right, so I'm here. That's my f of x given A1x. And hopefully by now, you know that this value is 1. So the average must be in the middle because I'm going to put myself a wedge here to see whether I can balance this. Okay, I balance this at half, of course. So this must be equal to half. And by the same token, this is 3/2, and I'm not going to do it. Okay? So I found a conditional probability density function, assuming that x between 0 and 1, which is the event A1. I found it. And just by eyeballing, I know that the mean is half. Okay? So this will actually allow us to compute the expectation. Okay, so the expectation of x by the total probability theorem is probability A1 multiplied by expectation value of x given A1 plus probability that A2 is happening, expectation value of x given A2. What is probability of A1 is 1/3. What is the expectation value of x given A1? Wicket says that it's half. So we'll put half plus 2/3 multiplied by 3/2. Okay, so this is 7/6. Okay, so this is a divide and conquer approach. We first divide the problem into 2 parts that are easy. Then we conquer each part and put them together. Understand? Right, David, why are you not here? Thank you for 1.5. Is this very clear now? Okay, so now we also want the variance, right? And I can show you that actually this approach is pretty powerful to get the variance. Now, if I want to get the variance, eventually I want to use the formula second moment minus first moment quantity squared. I already have the first moment. So I want to get my hands on the second moment, which is expected value of x squared. So we can apply the same approach and we can write down this law of total probability to the second moment. There's nothing stopping us from putting squares here. Okay, we can put squares here. X squared. x squared like this. Okay, and this is 1/3, and this one is 2/3. All right, so we need to figure out the second moment, okay, of x, given that I know that x is between 0 and 1 and in the other interval. Right, so from a previous calculation that I did, maybe a couple of weeks ago, the second moment, I'm just going to write this down, of a random variable uniform on the interval AB is a squared plus AB plus b squared over 3. Okay, this is a tedious calculation that I will not do. Okay, if you want me to do this calculation, I can do it for you offline. But you can check this for yourself. So I have a certain random variable z that is uniform on the interval AB. The claim is that expected value of z squared is equal to exactly this. Okay. Actually, this can be found from Wikipedia. I don't remember these things. Okay. But now, okay, if we have a random variable x, if the random variable x takes on values between 0 and 1, that means we are in A1. We have this shape here for the conditional density. So the second moment, the b is 1 and the a is 0. So we can substitute into this formula. 0, okay, so it's 1/3. Okay, because b is 1, a is 0, so all this go away, 1/3. Okay, so the next one here is, well, we are uniform between 1 and 2. So this is our a and that is our b, all right? So this is going to be 1 plus 2 plus 2 squared over 3. Okay, so that yields 7 over, all these things yield 15 over 9. Okay, so now by plugging into the variance formula concerning second moment minus first moment quantity squared, we have 15 over 9 minus 7 over 6, or squared. This is going to be 11 over 36. Okay, so here the point, right, is that I'm adopting a divide and conquer approach. I know some formulas regarding uniform distributions. If I have a uniform PDF, the mean is in the middle, and the second moment is given by this strange formula that you can derive. So I just have to identify now, conditioned on A1, what is my A and B? It's 0 and 1. Condition on A2, I'm uniform on 1, 2. So my A is 1, my B is 2. So I substitute into this particular formula to get this part here. Then I carry out this calculation, I get something, and then I plug into the variance formula, which is second moment minus first moment squared, and I get some number. All right, the number does not matter. What that matters is you know how to use the divide and conquer approach. Got it? So all these examples are in the book, you can review it, okay? Yeah. Today, I don't need to spend all the 2 hours. I will talk about one last thing and then we can call it a day. There's no rush, okay? So does anyone have any questions on this calculation? So we divide and conquer into 2 segments. And each of these 2 segments, it becomes uniform. The density is uniform. Of course, you can go and compute the variance by looking at this whole thing on its own, and you should do it and check that the answer is the same. It requires some integration. Here, I just have to recall that the second moment is this. This can be found on Wikipedia. Right. So the last thing I want to talk about, if you allow me to indulge you, all right, is the independence of 2 continuous random variables. Continuous random variables. All right. So we say that x and y, which are joint continuous random variables, we say that they are independent if their joint probability density function factorizes into the product of the marginals. for all xy. Okay, so now this is the same as the following. Okay, it's the same as, you can write this in terms of conditionals as well. Okay, f of x given y is equal to f of x without conditioning on y for all y such that f of y is bigger than 0. Okay, so this is the same. Okay, and the reason for that is because if we don't assume independence, then this can be written just using base rule, right? As f of xx, f of y given x, y, I mean to do f of x given y. If we don't assume anything, then we have this. Okay, so if fyy is greater than 0, then we can cancel on both sides, and an equivalent condition is basically this, which I've written down here. So here, this red part is not assuming anything, not assuming independence. But if it holds that we are assuming independence, then this part must be equal, this part, which is this part, must be equal to this part here. Right? Because we can cancel out the fyy. Does that make sense? So this is the same as the discrete case and same as everything that we have talked about. All right. So finally, we can also say it's symmetrically, there's nothing special about x and y. Symmetrically, right? X independent of y. This symbol means independent. X is independent of y if f of y given x is equal to fy y for all x such that the marginal is positive. So for example, if Vanessa or someone told me that x is equal to x, that does not change my belief about y. Okay, so that is the meaning of independence, right? Okay. Okay. So just to illustrate this definition, let's look at one final example for today. All right. So here x and y are independent Gaussian random variables. And the expected value of x is equal to, say, mu x. The variance of x is equal to sigma x squared. The expected value of y is equal to mu y. And the variance of y is equal to sigma y squared. So we can write down the densities of x and y because they are all Gaussians. And I've written it for you just now. 1 over square root 2 pi sigma x e to the minus x minus mu x quantity squared over 2 sigma x squared, and fyy is the same thing except that you toggle the values of x and y. E to the minus y minus mu y squared over 2 sigma y squared. So those are the densities of two Gaussians. Now, if they are independent, since x is independent of y, we can write down the joint as a product of the marginals. So it's the product of these two guys. So this is equal to this multiplied by this part here. We can just write down the product. Okay, so we have this. Okay, so basically we can multiply this, but now we can simplify this a little bit because, okay, this is nothing but the marginal density of x. This is the marginal density of y. And we can now rearrange all these things to make them look good. 1 over 2 pi sigma x sigma y e to the minus x minus mu x squared over 2 sigma x squared minus, or we can plus here, y minus mu y quantity squared over 2 sigma y squared, right? So this is the joint density of a two-dimensional Gaussian for which the X and Y are independent. All right. So what are the contours here? So this has the shape. Just mentioned that this has the shape of a bell centered at mu X, mu Y. All right. This has the following contours. Say mu X and mu Y are positive. Contours means lines of equal probability. Right. So it's X and Y. And our mu X, mu Y is here. Maybe I will draw this way. Mu X and mu Y, they're here. Okay, so this Gaussian, multivariate Gaussian, can be illustrated using contours of this form. Not very nice. So these are the set of points with equal probability. Okay, so these are all axes aligned because they are independent, and so on and so forth. Okay, and the spread in this direction is governed by sigma x. The spread in this other direction, which seems to be smaller, is sigma y. Okay, so these are basically the contours of the joint PDF. Right, so the levels you have equal probability. All right, so you can illustrate this using contour in MATLAB. Right, you can use the function contour. You can illustrate this using mesh as well. You can draw three-dimensional pictures if you want, but I cannot draw three-dimensional Gaussians here. Okay, so these are basically what I want to talk about for the section 3.5. Next time we'll wrap up the continuous random variables discussion. But before that, we will have a quiz on Tuesday. All right, then we'll wrap up the discussion on continuous random variables on Thursday. Okay. So I know we have covered a lot, but unfortunately, we have to cover a lot. So we cannot escape all this, but don't worry, if you don't understand anything, I can explain. I can explain anything. Okay, does anyone have any questions in the Zoom? Anywhere? When I say I can explain anything, I really mean I can explain anything. I also explain kindergarten school math. I have kids. I can explain anything. Yeah. All right. So thank you very much for your kind attention, and I'll see you on Tuesday for the quiz. Everyone has to show up, but I'll send another email with the precise instructions. Right. Thank you very much. See you. You don't think what is very hard? My class